right, so OpenMP for an accelerated world. So we're going to talk about OpenMP in the modern architecture world. My name is James Beyer. I work for NVIDIA. I've been involved with OpenMP for quite a long time now, previously with Cray as their OpenMP representative. Yes, so OpenMP on accelerators. Why is it so important? And the biggest reason here is the top 16 machines on the Green 500 use accelerators. Even with the new Green 500, even more accelerators are there. It's the only way to go green these days is to use accelerators. The Exascale subcommittee, quite a while ago, I don't think I have the date, actually produced a report, and these were the three key challenges they saw: power requirements, exploiting massive parallelism, and coping with runtime errors. Well, we can deal with accelerators, can solve two of those problems. They give you power, much reduced power, and they're massively parallel. So the other thing, why is OpenMP doing this? OpenMP is the de facto standard for parallel programming. It says shared memory. Most people think of shared memory as different than accelerator shared memory, but it's shared memory nonetheless. We just expose it in a slightly different way. All right, so it's a quick, OpenMP has supported accelerators since 4.0, 4.5 added stuff, 5.0 is going to add even more stuff. We're just going to talk primarily about what's in TR6, which is 5.0. Array of structures containing arrays, or this simple structure here. So we have a pointer inside of a structure. We're going to map this structure, and then we're going to map the pointer for that structure. But there's going to be a problem right now in the old definition of things, because this mapping would not attach. So when you made this call, down here, this P is actually going to be a host address, not a device address. So before TR6 or 5.0, fix-up code would have looked something like this. You would have actually had to snap that pointer into another pointer, map it, update it yourself. But this still has a problem. I made a mistake and I forgot to clean up the pointer s.p. So I need yet another snap to remember this saved value, so that when s.p gets copied back off the device onto the host, we haven't mutilated a pointer. So all that work is now solved by pointer attachment, a top-down approach to doing this. Now when you do the mapping, map S, then map s.p, this s.p will be moved to the device and then it will be attached. So inside of this region, s.p actually points correctly to the device address, and when you make the call, this s.p points to the correct address on the device. When we leave, we will clean up properly, so we'll release the memory on the device and then we'll detach. And part of what the detachment does is make the copy of s.p point to the correct thing on the host again. So when copy out occurs, you get the right addresses. All right, so UserDefinedMapper. So this is yet another more powerful way of doing what I just showed you. And so now we can declare a mapper. And this mapper says map s.a, map f.p, use length. So we have all this fancy thing. Then when we do map s, all that's going to happen here is s will be mapped, s.a will be mapped, s.p will be mapped, s.length will get first privatized. Then the s.p is going to be attached so that when you do this call, it will be the proper address again. And when you free, everything gets undone properly. All right, function availability. The biggest problem that we heard for people trying to program these things is the amount of data of directives they had to add to their code just to be able to get all the functions they needed available on the device. And this is why. So you have to put a pragma in here to say put this on the device. I have to put a pragma in here to say put this on the device. And then I have a target region that actually finally uses one of these. The whole problem with this is the users don't like adding this, especially when you have hundreds or thousands of tiny little functions in your source code. And the compiler can easily see, okay, the target construct contains this, so I know that I can back off and find this and recompile it correctly. And this one is being compiled for the device, so I can go find this and compile it correctly. So that's what we've actually asked the compilers to do is when you go through the code, whenever you hit a target, find these things, go back and look, have I compiled them in this function, are in this compilation unit, file, whatever you want to call it. Is it available to be recompiled correctly for the device? If it's not available, it's still up to the programmer to get the proper declared target constructs on there. But if it is available, they don't have to add any directives. Inferred function mapping is what I just described. So it's you needed it, otherwise you have to make your code ugly. That's what it boils down to. So this is what you end up with. Your code looks like this. You just put your pragma in there, and these things magically get compiled for the device because they were available. All right, data availability. This is a big problem. The map types, we have to, from, whatever. We have all this mapping that we have to do. We even add a modifier so we can guarantee that we update your data when we need to. Come on, let's go. We also have, so we have the target data, enter target data, exit target data, target update, declare target. We have all these directives. So right in 4.5, if you wanted 8 on the device, which as a global, you'd have to declare it as a target object. If you want B on the device, same thing. If you want big array on the device, you probably don't always want it there, so you would put it as link. So this is all just getting the data so you can compile and link to global objects. Then when you're going to use the data in a target region, you'd still list the mappings. These are just no-ops. The big array actually gets a slice moved over to the device, it gets updated, and then this link says that the global object big array should now point to what was just moved over to the device, so that when you make a call later that uses big array as a global object, it will work correctly. And the just point here is the always clause. So if you say always, to, from, A and B do get updated, and array is just treated the same way it was here. You still get the data movement, allocation, and everything. But the whole point is, this is a lot of code to have to write. So what we did is we added device profiles. And what the programmer says with the device profiles, this is what I require of the compiler and the target to get the correct results. It's a simple, OMP requires the unified address, unified shared memory. Unified address just guarantees that every address in the program will be unique. Unified shared memory means every address is both unique and accessible by every thread or every execution unit available to the device. One thing to make sure of here is scalars are always first private. So if the user wants them to not be first private, they need to say something, even though they may have removed other directives. So previously we had a whole bunch of directives. We had a directive for A, B, and big array, and we had data movement clauses on the target, just so that we could get all these things properly set up. Now all we do is say OMP requires unified shared memory. Now target can touch any of these things any way it wants to, and it's up to the implementation to make them available however it makes them available. For NVIDIA, that means that we would page in the pieces of big array as they're touched. It's small enough, it's probably 1 page unless it crosses a page boundary, so 2 pages. But all the linking, everything just magically works. No heavy lifting done by the programmer anymore. So the whole point of this is to say OpenMP programming for accelerators has gotten a lot easier. You have pointer attachment, you have user-defined mappers, inferred function mapping, and the device profiles, all of which make for a much cleaner first go at programming on Fluid Accelerator. Questions? Yes. So does a compiler support the TR6? No. So this is all TR6 stuff. So the IBM compiler supports OpenMP 4.0 and 4.5. It's a Clang-based compiler, and they have their I think it's called XL, their proprietary compiler. Intel supports it for their targets. GCC has some supports for it. PGI has announced that they're going to support 4.5. They have released the 4.5 mostly. I don't know if it's complete for CPUs, but not for the GPU yet. The GPU has been announced for next year.
So there's basically no
The Clang compiler. But these features aren't available yet in Clang, but Clang compiler for 4.5 is out there. It works amazingly well compared to a few years ago when they first released it. They fixed the holes that we told them they needed to fix. I'm sure they have more holes. We just haven't found them yet. Okay.
When you use a Pragma, it is behind the scenes is using the NVIDIA compiler, so you don't need to actually do.
So the Pragma is, when you use a Pragma, what it does is it gives the compiler extra information. And so when you put a Pragma on a loop, if you say parallel 4, you're telling the compiler that this loop should be run in parallel and work shared across whatever threads you apply to it. You can also do that with target, which target says take this block of code and go run it someplace else as a task. And that's what gets you onto an NVIDIA device. Yep.
So if you have a physical machine with an NVIDIA
Yep.
processor, you will actually.
Yeah, we'll actually be able to make use of it. Yep. You'd have to get right now the only compiler that you could use would be the Clang compiler, and you have to actually get parts of that Clang compiler from the IBM Yorktown repository because they have things over in that repository that haven't made it directly into Clang yet. But it's all available. It's all open source. Okay. Thank you.